So what we're going to look at briefly this afternoon, we're going to look at a few things. We're going to look at force, Pascal's principle. Then we're going to look at Archimedes' principle. Archimedes' principle. Right? And related to this, we're going to talk a little bit about what we call the law of flotation. Flotation. That's an I, flotation, right? So we're going to talk a little bit about how things float, why they float, and all of that, right? So we're going to talk about those two things. I think the notes I sent to you did have something about fluids in motion. Maybe you could disregard that. We're not going to cover that. That's a bit more complex. It's interesting reading. I left it there because for those of you, as you said, some people love physics. And, you know, understanding perhaps why, like an aeroplane, why is there, you know, when the engine runs and it propels air, you know, passes air over the wings of the airplane, how that pressure difference is created and causes lift as well as a forward movement. That's nice to know, you know, and it's there. But it's not, I wouldn't get into that for this course. Because what we're dealing with here is more of fluids at rest, right? Not fluids in motion, right? Or the statics of fluid or fluid statics. That is fluids that are just at rest, they're not moving. Fluid dynamics, that is much more complex, but it's very useful in real life, right? As I said, you know, planes and so fly. I think one of the boys asked me the question about how is it that a ship or a boat can still traverse or advance upstream, or sometimes into the wind, right? The wind can be blowing directly against the boat, and yet it can progress upstream. That's heavy stuff, and that involves some fluid dynamics, right? Not the fluid statics. Fluid statics can't explain that, right? So let's do this little bit here, right? And let's start with Pascal's principle. And I'll just give you a little. Let's see if I can. So we're starting with Pascal's principle, right? And I want to share with you a very practical setup that I think you probably visited a mechanic shop and you see this, right? You see this sort of thing. Give me a second. See if I can snip it. I'll bring it home. Yeah. Yeah. I don't know if you ever see this kind of setup. Not exactly this, but a little piece of equipment that they have inside of a lot. Well, some of those established mechanic shops, right? Anybody ever saw something like this where they take the car in and there's a little mechanism there. It doesn't look exactly like you see here, but the whole idea is that they have a little piece of equipment and they put the vehicle on it. And a little guy would be cranking the thing with his hand, maybe. Some of them are hand crank, some of them, they'd actually have a little bit of an electrical mechanism that would cause it to make the car rise up into the air. And they can go at the bottom of the car now and see what's going on. Anybody ever visited a shop and they did that with your vehicle?
Yes, sir.
Yeah,
Yes,
sometimes
sir.
let me just yeah, it looks like this here. So they have okay, something here and then something here, right? And there's some kind of mechanism down here that goes under the car. So here's the car. Okay, well, this is the ground, right? This is the ground here. The wheel is here. All right. Sometimes they take out the wheel and all of that. And this little mechanism here, they'll do something, and then next thing you know, this thing just goes up, right? Goes up. And the car is in the air. Well, it's really this, right? It's really this, but this is simplified. What I have there with a car, and so it's oversimplified, right? For you to understand the physics behind it. And you have the car lifted up into the air now, and they can go underneath and see what's going on. And so whether your brake line is cut or whatever is happening under there, right? Yeah. So this here is based on what we call Pascal principle, right? And let me just bring over what Pascal principle is all about. Or let me go back and I want to get rid of. Yeah. Pascal principle basically is saying that okay. I don't know why this. Hmm. All right. Yeah. I'll come back to that. Yeah. This is what Pascal's principle is saying. It's actually saying that if you have a change in the pressure applied to a enclosed fluid, that pressure is going to be transmitted to all parts of the fluid. So if there's a change in pressure in one part, it's going to transmit throughout um, the liquid, right? Or any fluid. It can be gas too, right? So Pascal actually came up with this relationship. And he said that, look, of course, he did this mathematically, right? They take some measurements and so of pressures and so. And this is what he found out. He found out that, okay, if the force in one area of the fluid divided by the area of the fluid that it takes up, right, is equals to the force in the other area of the fluid over the mathematical or the magnitude of the area in that area, right? So if I were to just, let me see if I can catch back this. See if I can take back this picture here. No, no. Yeah. Ah, man. I think I have to more use maybe yeah. All right, let me get it here. Yeah. So looking at this diagram here, right? And if we were to rearrange this whole arrangement here, right? What you would see here, I wonder what this is all about. Yeah. If you were to rearrange the formula, you will have F2 equal to F1 over A2 over A1, right? If you take this and you rearrange it, you get that, right? Mathematically. So if you want to create a large force capable of lifting this car up, right? You want to create a very large force that would virtually lift up this car. You could use a very small force, right? I mean, comparatively small. But this is the part of the formula that you can manipulate. The area or the cross-sectional area here as compared to the cross-sectional area here. The larger this area here, right? The larger this area here compared to this area is going to multiply this force, right? So let's say the area of this part here compared to this part, it's 10 times. It's 10 times, right? A2 over A1 is 10. What it does to this force, it multiplies the effect of this small force. So if you want to create, let's say, 10,000, you only have to, newtons, you only have to have one, what is that? 1,000 Newton here, right? 1,000. And because of the relationship of these two areas, if it's A2 over A1 is 10, right? You can actually exert a force of 10,000 newtons over here. This F2 that you're seeing here is going to be multiplied by 10. And based on that, this principle, right? And it's true. It's generally true. I think in all of this, they didn't take into consideration all the weight of these pistons and so, right? They didn't take into consideration all that, but forget that. That's complex physics. But you can actually then multiply the effect of a small force. And that's why, I don't know if y'all probably change a tire. Those small jacks. Oh yeah, I should have used that instead of the one in the mechanic shop. Most of you here, you know that small jack that you use to jack up the car? Most of you own one of that, right? And they have a little lever like, and you crank it with your hand. And do you put a lot of force into that thing? Anybody use it before?
Yes, sir.
Yeah, do you exert a lot of force on the little lever that you use to pump the oil?
Yes, sir. It takes a great lot of effort.
Oh, really?
Yeah.
All right, compared to what is needed to lift a car. Anybody else? This one guy is saying it's hard to kind of work the lever to get a car lifted. Is that true?
Sure, they have different types. They have the one that has the long part that you just press and it go up, and then they have the smaller one, something like um wind it up or something like that.
Yeah,
The
but
one
what I'm
is
asking
more
is, all right,
effort.
yeah, some of them use a screw, some of them use a lever that you would crank, right? Maybe I need to go get a picture for y'all. Car jack. Let me go. But I don't get that. You're telling me that it's a hard thing to work? I'm talking about the force you exert, right? Compared to the force needed to lift the car. You can lift the car with your bare hands.
No?
No, but you do it with that little lever, right? Let me give you the a picture here. I just found one. All right, this is the one I have. I should have brought my jack, man. All right, let me see if I can take a picture of this thing here. Bring it over. Some of you, like, you need to get out of the office and the man says a hard thing. I find that very strange. All right, let me go. Let me go. All right, let me come here.
We're probably gonna mix up there because
This here.
the one that
Okay.
oh
So
yeah.
you put in a little bit of you put in there's a little crank, like a little handle then. You put in here, right? And you crank it with your hand. Click, 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 click. And this screw here, it kind of goes up, up, up. This piston here, right? Or that screw here. You could adjust that screw, but this piston here is shunting here. Actually lifts a car. I have a 2-ton car. And I would lift it with just cranking this thing about 4 or 5 times. So, all right, you notice this jack mark 20 ton? It means that this jack can lift up 20 tons. Can anybody lift 20 tons with their hands? Anybody in the class? I want to get this clear. If you don't understand the principle, you wouldn't get it. Nobody can lift 20 tons, but you do lift a 20-ton weight by just putting the lever in this thing here and you crank. You crank with about what? Maybe a couple hundred newtons, and you lift 20 tons, right? And that's the idea. You notice here, well, what is happening? All right. It's not showing here, but where this in this tube here, in this part of the crank, you notice how the area is small? Y'all notice that? Good. So
Yes,
what's
sir.
here? This bore here. The cross-sectional area of the bore is very small, but look at the cross-sectional area here. Right? This is probably cross-sectional area here. It's probably about 100 times the cross-sectional area here. Right? It's like this compared to this. This looks like 100 times that. Times 100. Right? That's all. So whatever force you exert on this small crank here is multiplied by let's say, all right, is multiplied by 100. You get what I'm saying? And that's what Pascal principle is saying. I wonder why the class seem like they're lost or something like that. Yeah, so that's the principle here, right? You could use a very small force, but if the equipment you're using, the area of this part here compared to this part here is a big diffraction. A2 over A1 is a very large number, probably 10, 100, as I showed you in this case here. In this case, this bore here, the cross section of this bore here, where you are cranking the oil inside there, right? And remember, there's oil inside this thing. So you're going to exert a small force here, and it's going to translate into a large force here. And granted, your hand is going to work a lot, but then you see the car moving little by little by little by little, right? So it doesn't move fast, but it moves slowly up. Speed is not what you want. You want to multiply force. And you have the car lifted up. Right? The other day, one of my posts on my house was rotten at the bottom. And I bought, I think it was a 10-ton jack. 10 or, yeah, I think so, 10 ton. And I actually lifted the whole house, the front. I lifted the whole thing up. And I cut out the bottom of the post and I put in a piece of wood and I painted up nice, and that's it. So I lifted my house up. Just imagine. Why? Go right back to Pascal's principle. Pascal's principle. Anybody? I remember talking to this class, and some people were saying how they worked in industry, and so anybody works with this kind of thing? Anybody works at maybe at a workshop where such a device is used? Nobody? Hmm. All right. All right. So something strange with the class this afternoon. We're not getting the kind of
So
we're not
probably
getting the
the
kind of
probably
yes.
the persons at work in the industry that you're speaking about is at work and get some.
Yeah, yeah. All right.
Because most time they work from 6 to 6.
Yeah. Well, that's the next thing, y'all gotta start get your union involved and so well, God knows if you have a union there. But oh my. Um, when you gotta work those long hours, um, I mean if you from time to time you do it, yes, but well, I wonder why this thing is. Let me see if I use Control V. Yeah, this is what I'm talking about. Yeah. You can't do that every day. You know, people forget something called family life and all of that. You know, um, you need to have some time to yourself and so on. You can't work from morning till night. You have to have time for the family, and that's why you want to develop yourself to the point where you don't have to work those long hours because of your skill and all of that and your knowledge. You could work for less hours, right? And then people must value you so much that they can't knock you off. You tell them, Mister, I'm not going to be working this day that late. You could tell the boss that, but he needs you so much he can't knock you off. You're so valued. All right, yeah. Look at this one. This is a simple example here, right? So they're describing a situation here, right? So you have a hydraulic mechanism trying to lift a car up, right? And the radius of the input piston, that's this piston here where you see F1 is, right? It's 0.012 of a meter. That's roughly, if I were to multiply that by 100, it's like 1.2 centimeters cross-sectional area, which seems to be like the jack we were just talking about, a red jack that I had up there, right? Yeah, very small. The radius where the car is a little bigger. It's about 15 cm, right? So it's about what's this? 1.2. Yeah, it's roughly about 10 times, a little more than 10 times, right? Yeah. And we have a car here, the car, and they even put in that plunger, that piston like that the car is going to rest on, right? The weight is 20,500. So you want to make sure that you can lift that that car, right? That has a weight of 20,500. So we're using the formula here, right? And F1, well, notice we rearrange the formula so you can find F1. In this case, you didn't want to find F2, you want to find F1. So F1 is going to be equal to F2 times A1 over A2. Notice a switch around, right? A switch around. It's not A2 over A1 this time. It's A1 over A2, right? If you know your little bit of mathematics, you'll understand why we have that, right? Good. So F1 then, you're putting all the numbers. F2 is 20,500. A1 is given us 0.012. A2 is given us 0.15. They put all those numbers in, right? Oh, by the way, that's the radius. Yeah, you have to find the area. Area is pi r square, right? That's the area of a circle, right? So they give you the radius, sorry. They give you the radius, you have to calculate the area, right? Put all those numbers in and look what happens. F1 turns out to be 131 newtons, which is not very much, right? Not very much. So you can virtually, let me put it in terms of, all right, you want to put this in terms of a mass then, right? If you divide this by 10, it's about 13 kilograms. Like what you would need, right? The amount of force that you would need to lift 13 kilograms. 13 kilograms is like what, 26, let me say about 30 pounds, roughly 30 pounds. So the weight you would like if you were to lift an equivalent of 30 pounds, you only need that to lift this big car. Just imagine, right? The amount of force you have to exert is less than lifting 30 pounds. All because of the physics. You know, this little device harnesses an idea in physics, and we can be able to lift that car, right? We're able to lift that car. And we can now work underneath it and so, you know. The mechanism they have is more practical. This one is very impractical. Lifting the car up there doesn't help you to see underneath. But the one they have in the workshops allows you to go underneath there. And mind you, they have certain mechanism that can kind of lock all these things in the position it is, right? So that the car weight, when you let go of the lever or whatever, right? The car weight don't press down back slowly and falls on the person's head working, right? And they have certain locking mechanism, right? That allows you where the car doesn't press down back and cause problems, right? Most of you know the car jack that we were talking about, right? For you to let go of the pressure and make the weight kind of press down back on the piston, this bigger piston here, you have to actually turn there's a little screw like, and it kind of lets go the pressure, you know, and then the weight just presses down back, all right? And so there are other safety mechanisms that aren't mentioned here, right, that have to be in place, right, so that can be possible. But this is a remarkable little device, but it's based on Pascal's principle, right? Well, I was trying to get if anybody works with this kind of thing, and no matter what, you know, you want to ensure that those extra bits I'm talking about, the safety aspect, in that there are certain things that you have to do, right, to ensure that this car doesn't come, you know, smashing down on your head, right? There are certain things that you have to observe, and you have to know your equipment, and some amount of training is necessary, right? While, yes, the science is saying this, but there's some mechanisms, as I said, that have to be in place, right? That have to be in place so that not while you're working under there, you know, somebody goes or something goes wrong, and next thing you know, the pressure is released and the car comes down on your head, right? Because I know the one I have outside, there's a red knob, like, you know, and when you want to release the pressure, you release the pressure on the car, and what happens? The car weight comes down and it presses down on the jack, right? And it comes right down. If you're under there and somebody releases it, well, then you know it's the problem, right? And that's why it's so important that anybody here does this kind of work. You go under the vehicle, and what do you suggest we do? So you jack up this car, it's in the air for, let's say, it's jacked up now to about, let's say, about 2 feet off the ground or 3 feet off the ground. What do you do as a safety precaution? So the car don't, I mean, let's say the jack fails or some foul play is involved. What can you do to ensure your safety? Let me see if you all are thinking and so now.
Sir, you can have a backup, like a fail safe, something to catch it in case the jack fails.
Bright idea, yeah. As a matter of fact, some people will have some blocks of wood, you know. They'll have some blocks of wood placed at certain appropriate positions under the car. So if the jack fails, which can happen, those are realities, yeah. The jack fails, or somebody don't like you in the workshop and they want to get rid of you, just come and turn the knob, the little red knob. Woo! And the thing comes down on you, you're dead under there, right? So yes, you are right in that some people have certain like wooden blocks, and before they go under the car, they have the blocks, you know, positioned in a way that if the car is to come down, it's not going to smash you under there, right? So don't get carried away and excited with the physics. and you forget, these safety aspects, right? Keep that in mind. Good. So this is a nice practical example. I want to move away from this now and talk a little about Archimedes' principle. Archimedes' principle, right? Archimedes, right? This was an old Greek scientist, huh? And Archimedes' principle basically says this. Let me chop it from the notes we had over here. Everybody can see that?
Yes, sir.
Yes,
Good.
sir.
So what Archimedes basically is saying, right, that when a body is immersed in a fluid, right, it will experience a certain amount of upthrust. That fluid is going to kind of push up at that body, right? And you can have two situations. Well, before I go to that, there's a really humorous story. Anybody knows the story about
Yes, sir.
Archimedes? You know the story.
Yeah.
What was it all about? Give me a little
Um,
bit there.
Basically, it was something like as if he was in a bathtub and he realized that when he goes into the bathtub, some amount of water is being displaced. And then he figured out that it's proportionally displaced.
Okay, yes, that's in a nutshell. The background to it was that the king, the king he was serving at the time, um, suspected or wanted to know, man, I'm giving these people to make jewelry for me, He would give goldsmiths to make jewelry for me. And he was wondering whether the goldsmiths would actually kind of dupe him and mix in certain other, maybe put in a lot of copper in the inside of the gold, and so he put the problem to the scientists and say, look, how can I know whether this gold crown I have is pure gold, or it has this percent of copper as compared to another gold crown that has so much more copper inside. You all know, right, that gold, while it's very dense and so malleable, you can beat it into very thin shapes and all of that. You have to add certain things inside, they add copper, they add tin, that's how you get white gold, for it to get a little bit more strength, right? If you were to take just pure 24 karat gold and make jewelry out of it, your jewelry is going to break very easily and all of that, right? So they normally put in copper or tin. Well, recently tin comes up, right? But long ago they used to use copper. Copper being the main metal where they were mixed into gold, right? But sometimes a goldsmith can overdo it, right? Most of the gold you see in the market these days are barely 12 karat. When they talk about 24 karat gold, that's pure gold, right? So what would happen now is even the goldsmiths that you deal with, right? If half of the material you have, right, is copper and half is gold, that's 12 karat gold. That's the cheapest. And you don't want to go less than that, because what would happen? The gold will turn green. You all ever notice that? The gold kind of turn green because the copper is too much in it. And the copper is corroding and then turning that green color you see there, right? That's copper oxide, right? So the more gold you use, the better, right? So you want to have maybe like okay, let's say what you call maybe 14 karat, 16 karat, 18 karat. You want more gold than the copper, right? so that your gold is going to look more like gold, it's going to not corrode and that sort of thing, right? Because if you have too much copper, some people got health issues with copper, right? They wear it, the next thing you know, they start scratching. Some people develop other health problems because of the copper in the gold, right? Yeah, so back to the story with the king. So the king wanted to know, well, man, am I being duped? How do I know, right? And there's where the problem facing Archimedes. How can I, of course, um, he wasn't allowed to melt down the thing and all of that, right? So what he found out, or he realized when he went into the bathtub, is that the upthrust that you experience when you immerse things in water, right, is going to depend on the weight of the thing. And remember, the weight of the thing would depend on the makeup of the metal, right? Remember, gold is very, very dense. Let me see if I can go back to the density. I wonder if gold was on it. Let me see. Gold. Gold has a density of 19,300 kilogram per meter cube. And what's copper? Copper is barely 8,000, sorry. What did I say just now? 1,900? Gold is 19,300, while copper is only 8,890. So copper is far less. It's less than half times as dense as gold. And therefore, right, a crown that is made of copper is going to experience, or it's going to, if you were to put them, let me just show you. There is one theory. Let me just draw that. Okay. There's one theory that Archimedes could have taken two identical containers with water, right? Have a balance here, no? Put up a balance here. And, okay, he has a balance. And you tie on the goal, you know, okay. The water is there, all right. So the thing will duck in water, right? And then, all right, up here, water. And you tie on the crown that is made of, let's say this one is copper. More copper, right? I mean, gold plus copper. Let's say this one is pure gold, right? Pure gold. What do you think will happen when he puts, okay, he starts off the experiment here. What do you think will happen? So
The
these
gold
two
that
crowns
really
are
comes-
identical, right? What will happen?
The heavier one, the one with made of pure gold, would go down.
Yes, and this one will go up. Yeah, right? As a matter of fact, you don't even need to put the thing in water. I would think just air, just immerse it in air and compare the two, right? And the pure gold is going to be heavier than one with gold plus copper. You understand? It's going to be heavier based on the density, right? Based on the density. So yeah, he didn't even need the fluid, right? He didn't need the fluid. I don't know why he insisted on it, but yeah, he came up with this idea and he was able to determine whether I don't know the true story, whether these things, their stories are told over and over and over, and you don't know what is fact from fiction anymore with these things. Yeah. So Archimedes came up with that idea that objects would experience a certain upthrust, right? They'd experience an upthrust, and that upthrust, it's related. Let me just go back and see if I can. In the notes, I think I gave you, I don't know if the formula is there somewhere in the notes. The upthrust, which they call the buoyant force. Buoyant. I think I spelled the word wrong here. Funny how this word is spelled, right? This word is spelled BU OY, the buoyant force experienced is actually equal to the density of the fluid times the volume displaced, the volume of the fluid displaced times G, right? That's a buoyant force that that is going to be exerted on this object that you immerse inside of a fluid, right? So whatever is the density of the fluid, it's water. How much volume is displaced, right? And G is acceleration due to gravity. So what this would mean is that when you immerse things in water, again, all right, if you were to take so this is water here, right? This is water. You were to put an object inside here, right? And you were to tie it to a string, and on this string had a force meter. You know those they're called Newton meter, right? A force measurer or a Newton meter, right? So you have a little. It resembles that thing that some people has. Okay, it has a hook here, you know, and the thing hook on there, and it will have a calibration here. So if you were to weigh this stone, let's say it's a stone, and you were to weigh it, and maybe it's let's say 1 kilogram. When you put it in water, when you put it in the fluid, it's not going to weigh 1 kilogram anymore, right? It's going to weigh a little less. Why? Because there's a buoyant force pushing up. It's pushing up on this object here, right? FB. It's going to push up on that object, and for that reason, I know the force. I mean, I think I'm giving you the raw. This is not this is a force measurer or a Newton meter, so it will normally register in newtons, right? So let's say the thing is 10 newtons, right? The weight of the object is 10 newtons. You might find that when you put it in a fluid, it's now 8 newtons. Why? Because it experiences a 2 Newton buoyant force, right? So now the weight of the object is just 8 newtons, right? It's a little lighter. And how that comes about? Well, it displaces fluids, right? And what happens is, okay, let me explain why that happens. So before the, let me see if I can draw that. Let me see if I can draw that. All right, so let's say the level, right? The level of the water here, it's there. So when you put the stone in here, right? All right. So you put a stone inside this water now, right? The water wouldn't be at this level anymore. No, it's going to be a little higher, right? It's going to be a little higher, right? So the water is going to come up to here now, a little higher than down here, right? Now this difference, because the water actually is a little higher, the pressure above here is going to push back at that water now, right? And that pressure is translated to that object, right? As a matter of fact, there is a pressure difference from here to here, right? There's a pressure difference. Remember we talked about that thing? P equal to H rho G, right? And that pressure difference is what is going to cause an upthrust force, right? Depending on the area. You know, okay, we use a spherical object here. But if you were to use a cylindrical object, you could actually calculate, right? You could actually calculate the pressure difference, right? And know that force that's going to push up on that object, right? We're not going to do too much of the mathematics, right? But I'm just showing you where that force originates, right? Because of this displaced water, remember the atmospheric pressure is pushing back at that water, right? And that's going to create a force that would give this object an upthrust, right? You can also think about it, the difference between the pressure up here and the pressure down there, right, creates an upthrust, pushing it upwards, right, because of that pressure difference. Now that we are, okay, by the way, and this has a lot of uses, right, a lot of uses. For those of you, well, anybody here lives at an area where they do cane cultivation?
Yes, sir.
And you would know that we make use of punts, right? You know punts? You hear of that word, punts?
Definitely.
Yeah, we make use of punts. And what we do is that we pack the cane in punts and we float them in the canals to the estate, right? And why? Because, you know, ponds would float very easily, right? And because of that upthrust and so, the amount of energy that is needed to pull the pond along is going to be far less than if you had to pack them in like they're doing in some areas now, where they're cutting the cane with machine and they're packing them into bins, and tractors have to pull them along the roadways, so they're causing more congestion, and the energy required might very well be more, right? So long ago, and they still do it here. I live near an estate right here. We use punts to move things around the back dam, right? And that, you know, that's a useful thing. For those of you, I don't know if any one of you here is into logging. If you work in the logging industry or any related industry to logging, you would see them using this idea as well. They take the timber and they strap them together and they throw them in the creek and then they pull it along, right? So that's how timber comes out of the Berbice River, out of the Kanji Creek, right where I live here, right? They'll haul hundreds of logs out, and a little what you call the thing, tug, they call it, a little tug would pull it, right? So they have it in water and they'll pull it. They also have people who would pack the timber on top of a pontoon, right? And they'll pull it out to the coast here, where we'll cut it up and make lumber for you to, you know, to make houses and all of that, right? So they make use of this idea of the upthrust that is going to be experienced by these objects in a fluid, right? It's going to be easier now. And those of you, I remember when I had to make I was making this house here, and I had to get the lumber from the street into a yard, but there was a canal in between. And I was worried, how are we going to lift the sills, you know, and so to get it across. And an old man passed by and he said, "Why y'all lifting this thing? Why y'all don't drag it over the canal?" I looked at the guy and you know, and we decided to do that. Two things. The canal, when we pulled it across, it was easier to pull across. And secondly, because of the modern water involved, the thing slide over very easily. We pulled it over the canal, pulled it in the man's yard, and we were able to, I mean, we had messy log afterwards. It was all wet and muddy, but it was easier for us because it was just myself and, if I remember well, two other friends, right? We couldn't lift those sills because my sill was what? I think was around 30 feet, right? They were 6 by 6 by 30. They were not easy to lift, right? I was young and strong then, though. And the boys that I had with me were also young and strong. But still, lifting a sill that was 6 by 6 by 30 was not an easy task. And we decided to follow the man's advice. We just threw it in the water and we pulled it over easily. And then because of the modern water, we just pull it with canvas and the thing slide up easily. I said, what? And you know, it was easily done, right? Yeah. But as a matter of fact, you know, the history of, even though Archimedes' principle, right, was known for so long, getting a you know, ships made of steel came much, much later, right? They used to make a lot of ships with wood, right? Remember that? They made ships with wood. I hear no response, but again, yes. But somebody, some smart Alec, and I want to just give you an example, right? Let me just give you a little example here. So let me just mention this here, right? That let's say you have a plate of steel, so a plate of steel, roughly, right? Let's say it's okay, 1 meter by 1 meter, and the thickness, right? The thickness of the steel is let's say, all right, 0.01 of a meter, right? Which is like what? Oh, that's too much. That's like 1 cm. That's rather thick. All right, let's go with that anyway. It's not a very good example. Good. So if you were to take this steel plate, right? This thing is about what? The volume of this thing, the volume will be about what? 1 by 1 by this will be what? 0.001 meter cube, right? That's the volume, V. And the density of steel is, what did we say? All right, let me go with a number like this, 7,850, right? The internet gave me this one. 7 kilograms per meter cube. So when you think of this here, right? The upthrust that is going to be experienced. All right, the mass of something like this. Let me go with the mass or the weight, right? The mass is going to be equal to, all right, 7,850 times 0.01 kilograms, right? Which is roughly 78.5 kilograms, right? Roughly that. I hope I'm getting all my numbers right.
Yes, sir, it's right.
Good. So the mass of this piece of steel is this. So the weight, if you were to multiply that 78.5 by, let me go with 10 now, just to give a nice number. 10, right? As acceleration due to gravity. It's going to be equal to 785 newtons. So that's the weight of this piece of steel. Now, if you take this thing and you put it in water, what will be the upthrust? Let me see if I can make it smaller. Good. So the weight of this steel is 785 newtons. The upthrust, we just talked about it, right? The buoyant force, the upthrust that it's going to experience. What's the formula we got? I just gave you it.
Density times the volume displaced times gravity.
Density of the fluid times the volume displaced equal, okay, times the G, right? Good. So let's take, okay, let's say we put this thing in water, right? Let's say we put this thing in water, right? What happens now? So let's see. The density of water is 1,000. Let me put it roughly that, times the volume displaced will be the same, 0.01 times, let's go with 10, right? And we'll get what? We'll get roughly 100 newtons.
Yes, sir, 100
Good.
newtons.
So look at this. The weight of this this steel plate is 785 newtons. The buoyant force or the upthrust is going to be 100 newtons. What do you expect to happen with this steel plate when you put it in water? Huh?
So it will float.
How will it float if the thing got a 785 newtons weight and the upthrust in this is just 100 newtons? It wouldn't float, it sink to the bottom. It will sink to the bottom because the buoyancy is only 100 newtons. So if 785 newtons acting down and 100 newton acting up, while the plate is going to feel, if you were to attach a scale to it, it's going to feel like 685 newtons because there's an upthrust force of that. The net force is going to act down and the thing is going to sink like dead weight. Right? However, you are noticing here that over and over we are talking about density. Right? We're talking about density. Right? And some smart Alec decided and they think that, man, what about if we take this steel plate, you know, and we were to bend it, like this. Right? And so all of here will be air, right? Will be air. And air has a density of, let me Google it. I think I Googled it. What's the density of air? Density of air is roughly 1 point. What do you have here? 1.225. That's what you have, right? Good. So what would happen now? When you look at the density of the material and compare it with the density of the air, right? So the material had a density of, what was it? 7,800 and was it 60 or 50 kilogram per meter cube, right? But when we think of the, how much is it?
7,850.
Oh, 50. All right, good. 50. Good. So because of the low density of air, the average density now here, remember what I didn't mention, and you're supposed to figure that out, that when an object is denser than water, it sinks. When an object is less dense than water, it tends to float, right? So because of this shape of this container now, right? You take the metal and you shape it like this. So you trap some air in here. So the overall density of this here, remember water, the density is 1,000 kilograms per meter cube, right? Per meter cube. So what you have, your aim then is to shape this container such that the density, right? The density of this container, the average density, not just the steel, but the air inside here must actually be less than 1,000 kilograms per meter cube. And once that happens, right? Once that happens, this container is going to float, right? It's going to float. Is that clear? So there's a bit of mathematics involved, right? As to how much air you would have to, because if you were to barely maybe do this, barely bend it to the end, it may not, the air in here may not be enough. So it will depend on the dimensions and so. I probably what if I should try? All right. Let me try with a bit of calculation and see if we can. All right. Just keep in mind at the corner here that water has a density of 1,000 kilogram per meter cube, right? Good. So just now we had a the steel plate down here. What was it? 785 newtons? 785 newtons. Let's keep that, right? Let's say we were to put on a wall like here, a wall here, right? If we were to put on a wall there, and let's say it's 1 meter high. I'm not sure whether it will work with 1 meter, but let's go with 1 meter, right? That's like about 3 feet. Good. So what we're going to try to do now, let's see if we can calculate. Let's see if we can calculate the what would that be? 1 meter by 1 meter by 1 meter. So we got 1 meter cube of air now, right? Is that right? Remember, the steel plate is 1 meter by 1 meter. I'm going to neglect the weight of the wall, right? Let's just neglect that just for simplicity's sake. So we have inside here 1 meter cube of air, right? Is that clear? So we want, let's say we want to weight now, the weight of the air. What will that be? The weight of the air is going to be 1.2. I should just use 1. All right, 1.225 by 1 meter cube, right? That's going to be by, let's go with 10, right? What will we get here? The weight of the air.
Sir, 12.25.
All right, 12.25 newtons. So the total, oh, and by the way, I must make a claim, make a point here. I'm not sure whether 1 meter here is going to make this thing float. I'm not sure about that, right? But I'm just using 1 meter, right? Good. So we end up with the total weight is equals to 700 and just add 78, sorry, 785 and 12. Leave out this 2.5, just add 12. 785 plus 12 is how much?
Sir, 797.
797. All right, good. So roughly 800 newtons, right? Approximately 800 newtons. That's now the weight of this thing. So what we're going to do now, we're going to calculate the upthrust, right? Upthrust. Now, what volume of water is going to be displaced? Well, remember we said the upthrust, FB, is going to be equal to, what's the thing? Density of the water, right? Multiplied by, what was it again? The volume of water.
The volume displacement
Multiplied by
times
G,
gravity.
right? So let's see what the upthrust is going to be. Density of water is 1,000. 1 meter cube of water is displaced when you put that thing in water. Multiply by 10. So we now have an upthrust of 10,000 newtons. Miracle of miracles now. You see that? The weight of the steel, the steel container that we made by putting on a bit of siding is 800 newtons. And the upthrust is 10,000. I think something is wrong here. Volume is 1. G is 10. I don't know. Something doesn't seem right. The numbers seem too fantastic. I wonder whether we missed something here. Yeah, anyways, the point is the upthrust is far more than this, than the weight of the object, the steel object. Right? And therefore it's going to float. right? So, something seems odd about this 10,000. 1,000 by 10 is 10,000. Yeah. Density of water is 1,000. The volume is 1 meter cube. Oh. All right. I think there's something I need to point out, right? That, okay, if you were to take this object, I want to point out something to you that probably you don't realize what's happening. If I were to take a big container of water and I take this object and force it down, right? And force it down into the, oh, by the way, if it's enclosed totally, that air in here, air inside. And I were to force it down into the water. The upthrust here, while the weight is 800 newtons, the upthrust is going to be 10,000 newtons. And have you ever tried this? You take like a bottle, a closed bottle, and push it down in water. Do you notice that something is pressing it up?
Yes, sir. It shoots back up.
Yes, sir.
Good. So I want to tell you now that our object, it's not going to actually experience this amount of upthrust unless we push it down underwater. What will happen is it's going to float, right? And when it floats, and that brings us to something else, the law of flotation. So it's not that if the water is going to exert 10,000 newtons on this thing, if you were to push it below the surface, it's going to experience that. But what's going to happen is that the water is going to push with whatever is needed to keep it afloat, because all this object needs is 800 newtons. So 800 newtons is going to press up on this object and it's going to float on top there. Now that brings us to the law of flotation, right? It's not going to exert 10,000 newtons, because what's going to happen is, let me show you what's going to happen. You have this big container of water, you put this object inside, right? You put this object, got air in here, air inside here, right? You're going to find that the object is going to float in this water, right? And the weight of it, which is around 800 newtons, the upthrust on it, just what is needed, the 800 newtons, is going to be exerted to keep it there. If you were to try to push the object below the surface, the full 10,000 newton is going to come into play, right? But just 800 of the upthrust is needed to keep it afloat. Now that brings us to the law of flotation, right? And what the law of flotation basically is saying, right? The law of flotation is basically saying that that an object that floats in a fluid displaces its weight, right? It displaces its weight, right? So that's a simple way of putting the law of flotation. So what happens is that once an object is floating in a fluid, the amount of fluid that it will displace will be equal to its weight, right? It's not a new law, right? I know sometimes some textbooks present the law of flotation as though it's a different law, but it's what there's a big word they use in thermodynamics called a corollary. A corollary is like a law that comes or a conclusion that comes from another, maybe a law or an observation or something, right? So the law of flotation simply stems, it's derived from the law or the principle of Archimedes, right? And basically what it's stating is that, let me cut it directly from what the internet has here, just to let's take this little bit here. One second, give me 1 second. Everything takes so long on this computer. All right, let me see if I can get it. All right. Yeah. Right. So this is a simple statement of the law of flotation, that a floating object displaces its own weight of the fluid in which it floats. Right. And it's not a new law, as this is saying. It really comes from Archimedes' principle. Right. So all that has to happen when an object floats is that the displaced fluid must equal to the weight of the object. Right. And one of the things, I don't know if you ever notice things floating in a fluid. Let's say water. Let me draw something here. So you have okay, this is water here. Does the thing float on top there like this? Does it float like that? Anything floats like that?
Sir.
Somebody saying yes, no, what are you saying?
Sir,
No, sir.
they're like the beach balls, the plastic balls.
They float on top like that?
Honestly, this is the closest thing I could find because it does kind of have a little bit inside the water, but it floats to the very top.
Sir, how about a bottle container?
No, anything that you're talking about. Well, there is very careful observation. Please, you can always do this on your own and see, right? It never floats like this, right? You always have situations like this where, okay, this is the fluid, and no matter how light the thing is, it's either there's always a piece. There's always a piece under there. There's always a piece under there, and I'll tell you why just now, right? As well as you can have a situation where the whole thing, it floats on top and the whole thing is submerged, right? Now, what determines how much of the thing is submerged? What determines that?
Sir, the
Well,
content of whatever it's inside of the weight.
Throughout our discussion, right? Throughout our discussion, you would notice that density is always involved, right? Density. And depending on the density, there's a formula. I want to just put that formula up here, right? Fraction, submerged. You can start with this spelling, right? Is equals to, all right, the volume submerged over the total volume is equals to the density of the object over the density of the fluid. Right? So the fraction that is going to be of the object that is going to be submerged, right? It depends on, and notice what I'm saying, the volume that is submerged over the total. And you want to know this really, right? So it's related to the density of the object over the density of the fluid, right? So if the density of the object is equal to the density of the fluid, maybe just a tiny bit less, you're going to have a situation where this is the fluid and the thing floats like that. If the two are almost equal, right? If the density of the object is far less than water, you're going to have, all right, the fluid, and most of it is going to be above. Even that beach ball, one of the girls talk about a beach ball, all right. The beach ball is going to get a tiny bit under the water there. Got to get something under the water there. Right? Tiny bit. I know you all are going to kill me and say, I'm sorry, the thing look like it is there on top. But there's a tiny bit under there based on this formula. Right? Based on the formula. You must have a piece under there. And that explains also, I'll send you a worked example on YouTube where you know icebergs? Why icebergs float like that? And they're telling you the most of it is underwater. And maybe a teensy-weensy bit up here is above the water. Think of this as an iceberg. Most of it is under there. The reason why is that the density of the iceberg is almost that of water. So that's why most of the iceberg is underwater, under the water. Right? And I'll send you a worked example to highlight that. Right? So now we're talking about this here, and I want to just touch on one bit before we close. Again, we're coming back to this matter of safety and so on. Does your work involve you traveling all over rivers? Rivers or water? Maybe you have to traverse, you have to go into maybe an interior location. Anybody here?
Yes, sir.
Okay, one person says that. Maybe a few of you, right? You'll have to travel. Maybe you have to come over the river with a speedboat. Some of you have to go into interior locations, all of that, right? Now, I'll tell you what, no matter how good a swimmer you are, let me tell you, I'm a very good swimmer. But I've learned the lesson. Never be confident, never be too confident in your swimming ability. And I'll tell you two situations. And I'm coming to the safety aspect now. When I just got married, my wife lives near the river. So I went to, visit my in-laws, and they said, come, let me see, if you can swim and all of that. So I went to the river corner. I was, kind of trying to impress the boys how well I can swim. I went out to the middle of the river, swim back in, and you wouldn't believe me. The very moment I was like, I was now reaching up to the boat, right? To the edge of the boat to pull myself into the boat. I kicked off, and guess what? I caught lock. You all know what lock or cramp?
Yes,
Anybody
sir.
knows what that? Yes, my foot caught cramp because maybe my salt content in the blood or whatever. I caught cramp. It was a good thing that my brother-in-law was right there, and he grabbed me and he said, "What happened to you?" I said, "Oh my!" I couldn't answer, and he pulled me in the boat. My foot, it couldn't move. The muscle was all cramped up. Just imagine if that happens to me in the middle of the river. I'd been a dead man during my honeymoon. Right? It happened to me on the beach as well. I went out one time and I was going way out where my feet was barely touching the bottom and my head was barely above water. And guess what? I got cramp again. Right? It taught me the lesson, don't be too confident in your ability to swim and all of that. And for that reason, one of the things you want to do when you do those trips, right? When you have to cross rivers and bodies of water, make sure you wear a life jacket. The reason why, simple. Just like when we went back to this floating business, when you attach a life jacket to you, right? Your average density overall, right? Decreases significantly. Right? Because that life jacket is part of you now. So the weight that is going to press you down compared to the upthrust that is acting on you is going to be far more, right? And therefore you can be pulled down under the water because of the density of the life jacket is very, very, they make it with a material that, the density is very light and it doesn't really absorb and keep water, right? If you notice what the life jacket is made of. So you are actually, the average density of you and that life jacket combined is far less than water. And that keeps you floating, right? So don't joke about it and, show yourself too overconfident. I know for swimming, I don't need that. No, right? Don't be too confident. Wear your life jacket, wear it. It could mean your life, right? I know of a friend who they were coming over the river, the Essequibo River, and it was a small boat, and the boat upturned, and you wouldn't believe me, their life jacket is what saved them, right? The boat upturned, and because they were all wearing life jacket, they were able to they got the boat, they tried to turn it over back and so, and they were able to get back in the boat, right? And they survived. I remember one time I was being foolish. I was coming from an occasion over the Bordis River, and the big boat, the ferry, was taking a long time. So we decided to get into a French fishing boat. And you wouldn't believe me, we had no life jacket. And we hadn't lights. You wouldn't believe me. We just had a torchlight. And there was this company, JP Knights, had these boats, these speed boats that would take workers out to the ocean there, right? And they were coming with full speed. Boy, that wave nearly swallowed us up, right? And the guys on the boat, the speedboat, started to quarrel that y'all are without life jacket, and look where you are in the middle of the river, hardly any light, That day, I realized, and imagine, you wouldn't believe me, it was me, my wife, and daughter. My entire family would have been swallowed up into that river because of stupidity, because of not being safe, right? So I hope those stories kind of bring out that don't be overconfident, make use of the life jacket, right? That's just one scenario, right? So make use of it if you ever have to use, the rivers, and so you have to cross the river or you have to go into the river for any kind of work, right? Life jacket kind of reduces your density overall and you float. All right, so I think we talked a lot there about Pascal's principle. We talked about Archimedes' principle and now the law of flotation, which came from Archimedes' principle. I'll send you a little video to watch for your, to see a worked example involving an iceberg, right? Hope you enjoy and benefit from it. So we'll stop there, right? I think I talked for what, 2 hours straight? All right. Let me see, how do I gotta stop the recording? Stop recording, yeah.